Okay, in this video we are going to cover the complex roots case. To start, I'm going to show you an example and what is the problem with this example. Okay, now the common procedure is to replace this with a characteristic equation. It's going to be m squared plus 4m plus 7 equal to 0. Okay, so think in two numbers in which the multiplication is 7 and the addition is 4. Okay, that is very difficult because multipliers of 7 is only 7 and 1. So combination of 7 and 1 to be equal to 4 is going to be very difficult. Because it's very difficult, then let's use the chicharronera. Okay. So using the chicharronera is going to be m1 and 2 is equal to minus b minus 4 plus minus the square root of 4, the square 16 minus 4 a and c, 1 times 7 over 2a, just 2 only. Okay, so So what we have here is minus 4 plus minus the square root of 16 minus 7 times 4 is 28. So 28 over 2. So that means that 16 minus 28 is going to be 12. Yeah, 12. So m1 and 2 is equal to minus 4 plus minus a square root of minus 12, and that is the issue. That is why we couldn't find two numbers, because they are in the imaginary roots. All right. Okay. So, but let's reduce this. Multipliers of 12 is going to be minus 3 times 4. Okay. We can take the square root of 4, so that is going to be minus 4 over 2. Plus minus a square root of minus 3, and the square root of 4 is equal to 2 over 2. So we cancel the 2, and minus 4 over 2 is just 2. So m1 and 2 is equal to minus 2 plus minus the square root of minus 3. I'm going to split that in the square root of 3 and then the imaginary number. If you remember, the imaginary number is just the square root of minus 1. Okay, so these are the roots, and we have the positive and the negative. So my roots will look like this. m1 is equal to minus 2 plus the square root of 3i, and the m2 is equal to minus 2 minus the square root of 3i. Imaginary number. Okay, now the first solution then, what is the first solution? The first solution is going to be exponential of minus 2 plus the square root of 3i x, and my second solution is going to be the exponential of minus 2 minus the square root of 3i x. So my homogeneous solution will be c1 exponential of minus 2 plus the square root of 3i x plus c2 exponential of minus 2 minus the square root of 3i x. And that's it. Okay, so we finished. So I don't see what is the problem. Okay, we do have a problem. Mathematically, this is correct, or it could be seen as correct. However, for engineering, in the engineering we don't like functions with imaginary numbers, because they cannot be measured. We cannot see them because they are in another dimension. Okay, even though this is correct, we want a different solution. Okay, so in the end we want real functions as solutions. imaginary functions are not useful for engineering. Okay, so that is the problem. So how are we going to fix this? How are we going to change this from imaginary functions into real functions and still be solution of the differential equation? Okay, to do so, we have to use the Euler equation. So I'm going to erase this part and do a generic case of imaginary roots. Okay? So this just was the example of what is the problem. And the problem is we have imaginary functions and we want real functions. Okay. Okay, so because we need a generic case, I'm going to use A, B, and C. Okay, because the characteristic equation will be AM squared plus BM plus C equal to 0. Okay, and the chicharronera is going to be equal to minus B plus minus the square root of B squared minus 4AC over 2A. Now, to have imaginary roots, what should happen is that B squared minus 4AC must be negative. So, in order to have the imaginary root. Now, if this number is imaginary, then we can write it like this. Minus B over 2A plus minus the square root of 4AC minus B squared over 2A, the imaginary number. I just factorize here the minus and calculate the square root of that minus and convert it into the imaginary number. Okay, now, because this is negative, if we flip this, then now it is positive. So, the common nomenclature of this is that this is the real part and this is the imaginary part of the complex number. So my two roots is going to be alpha plus minus beta I, where alpha is the real part, alpha, and the imaginary part is the beta. Okay, so instead of writing these long numbers, I'm going to just replace by alpha and beta. Okay, so my first solution will be exponential of alpha plus beta I x. And my second solution is going to be exponential of alpha minus beta I x. Now, pay attention that the only difference between the first solution and the second solution is just this is positive and this is negative. This is called the conjugate. Okay? Okay, so I think we can split this exponential into exponential of alpha x times exponential of beta xi. The same in the other exponential of alpha x times exponential of minus beta xi. Okay, so as you can see here, this is the same for both solutions. The only difference here is that this is positive and this is just negative, minus beta x. And I write it like this because I'm going to use the Euler formula. The Euler formula goes like this. The exponential of theta I is equal to the cosine of theta plus I sine of theta. Now, in the case when you have a negative, minus theta I is just cosine of theta minus I sine of theta. So the only difference between the positive and the negative is that here it changes from positive to negative. So what I'm going to do is replace these two formulas here, assuming that this is theta and this is minus theta, of course. Okay, so if we do that, then my first solution is going to be exponential of alpha x. We didn't change this, but we are going to change is this. So theta is beta x, so it's going to be cosine of beta x plus I sine of beta x. My second solution is going to be exponential of alpha x. Remember, this part is the same. The difference is in this part. Cosine of beta x minus I the sine of beta x. Okay, the same difference as in the beginning. The only difference is here is positive and here is negative. Still, on this solution, which is the same, here is positive and here is negative. Yet here is still imaginary function. We still have the imaginary solution. Okay, now, so how do we get real solutions? What we are going to do is this. We are going to do y1 star, another solution, y1 star, and we are going to do a new solution out of these two solutions. I'm going to do first solution plus the second solution. And let's see what happens. If we add these two, we have the exponential is the same. The exponential of alpha x, we can actually factorize it. But if we factorize here, then this is left. So if we add these two together, it's going to be 2 the cosine of beta x. But what about this one? This is positive, this is negative, so it's going to be plus 0. So here is only 2 times exponential of alpha x cosine of beta x. And what we got here is a new solution, but it doesn't contain the imaginary number. It's just real numbers, real functions. And we are actually interested only in the solutions, in the function solution, not in the coefficient. The coefficient is going to be a constant, so we don't care about these two. What we care is about the real functions. All right? So this is our y1 star, or new solution, which is real functions. Okay, now, what about if we do the opposite? Y2 star, my second solution, but instead of making the addition, now we do the subtraction, y1 minus y2. Okay, so it's going to be this minus this. So what will happen is that the exponential is still the same, exponential of alpha x, the real part is this, so it's going to be the same. So now it's going to be this minus this, so it's going to be 0 on this cosine, and then this minus this is going to be minus 2, no, sorry, plus, because minus times minus positive, plus 2I the sine of beta x. Okay, so what is left here is 2I exponential of alpha x sine of beta x. And this is going to become my second solution. Okay, what I do care, I don't care about this coefficient. What I do care is that the functions are real. Alright? Okay, so these are the formulas, engineers. The first solution is going to be, my first solution is going to be, my first solution is going to be exponential of alpha x cosine of beta x, and my second solution is going to be exponential of alpha x sine of beta x. So these are the formulas you are going to use, and the homogeneous solution is going to be the linear combination of these two solutions. So it's going to be c1 exponential of alpha x cosine of beta x plus c2 exponential of alpha x sine of beta x. I usually factorize the exponential, so the homogeneous solution is going to be exponential of alpha x times c1 cosine of beta x plus c2 sine of beta x, because the exponential of alpha x is the same in both solutions. Okay, so these are the solutions, and you can see here we have real functions. We no longer have imaginary functions. Now, where this imaginary number disappear? Well, when we were only interested on the real solution, because this in the end is just a constant, and a constant it is here. Okay, so these are the formulas to find the solutions for complex roots when you have imaginary roots. So here you have the two solutions, alpha plus minus beta I, and the solution is here. The positive is the cosine and the negative is the sine. So in sort of speaking, alright? So this is the formulas. Next video we are going to do a summary of the three cases with an example below, alright? See you in the next video.